Good evening, everyone. This is Celso Batalha. I attend the internet course at Evergreen Valley College, and we are today entering the realm of stars. We studied yesterday the sun, and the day before also solar properties. So we learned the sun as a star, and now we are looking a little bit further and trying to decipher how can we determine the properties of stars out there. Um, so what we have built so far that enable us to do this trip and build up knowledge about stars that are so far away, we haven't have yet the technology to travel to these places. So how do we know so much about stars, about the universe that is so far away that we have not touched it yet? Hey Charles, can you hear me now? Oh, I can hear you. Can you hear me? Uh, Charles, your microphone is on. Okay. Um, I'm taping now. If you could mute your phone. Hey, Charles, could you mute your phone? There's some background sound going through.
Sorry about that.
No problem. There you go. So how do we know about objects, stars, or later on about galaxies that are so far away we haven't yet had developed the technology to go to these places? So how do we know about them? So the tools we have that enable us to establish knowledge about these objects, how hot they are, how big they are, how about their evolution, how they were formed, and how they are going to end their, if you would call, existence, and what is the main purpose of their process, their evolutionary process. What is the end product of stellar evolution? So the tools we have, the tools we are equipped to know about stars are called spectroscopy and photometry. So this chapter 17 and chapter 18 give us the techniques astronomers use to do measurement. We don't have a ruler that are big enough to establish distance from the sun to a star nearby. So the techniques we use require the knowledge of light. So light is the only um, messenger, if you will, of the stars towards us. So the light we receive in telescopes, and that's why chapter 4 was so important, because light interact with the stellar atmosphere of these faraway objects, and by interacting with the stellar atmosphere, it get imprinted in it the properties of this atmosphere. So when we collect the light that have been interacting with the atmospheric gas of stars, when we collect the light, we are able to trace back the history of that star to find out how hot that star is, how metal rich that star is, how which evolutionary stage that star is, and by doing so we can build up a story about this object. So let's initiate in chapter 17. There are two quantities, physical quantities, that you must be able to identify and to know the difference. One is luminosity, and the other one is the apparent brightness. So those are apparently the same thing, but they are not, and they indicate completely different quantities. Not completely different, but somewhat different quantities. So luminosity, the word luminosity establishes how much energy how much energy that star intrinsically put out in space per amount of time. So if you think about luminosity, we are thinking about energy the star is putting out per second. For instance, when we go in Home Depot, we might buy a 60 watts or ACE. I mean, it doesn't matter where you go. Safeway, Lucky's. So you buy a 60 watts light bulb, or you can buy a 100 watts light bulb. So watts is a unity that gives us the amount of energy that is being radiated per time. So you can think of stars as having certain amount of watts. So stars radiate certain amount of energy per time. Okay. So if you take a 100 watts light bulb and place next to you together with a 40 watts light bulb, certainly the 100 watts light bulb will appear much brighter. Now I'm using the word brightness. Okay. Now, if you take this 100 watts light bulb and you place on the top of a faraway mountain or faraway hill, so San Jose is surrounded by hills. So let's say you devise the farther away hill that you can see, and then on the top of it, and on the hill crest, you have this 100 watts light bulb set on a pole, so you can see from afar. And close to you, you hold this 40 watts light bulb. So which one is the apparent carry the apparent brightness now? So certainly is the 40 watts light bulb. Okay. So although the 100 watts is the most energetic of the two, the 40 watts appear brighter because it's closest to us. Okay. So on the same token, so light bulbs, they have the same size. So imagine we have a different ball game. We take, for instance, a light bulb that can radiate per area a certain amount of energy that is equivalent to that of the 40 watts light bulb, smaller one. Okay. Now, so imagine each wall of a 40 watts light bulb. Imagine the area that covers a 40 watts light bulb. And now imagine that you could build a light bulb that is several times in diameter bigger than the normal regular 40 watts light bulb diameter. More so that you could somehow manage that every square inch of that surface radiates the same amount of luminosity or energy that radiates on a square inch of the 40 watts light bulb. So I hope you can picture that a 40 watts close to you and a bigger, giant display of light that have the
Alert from
ability.
System UI Server.
Oops.
Low battery.
I don't know. My computer is always lacking battery at the end of the day. Sorry about that. So if you take now these two light bulbs or these two source of energy, one is a light bulb, the other don't know what it is. It's just a big thing that have the property of radiating the same amount of energy per square inch. Certainly, the bigger one will send out to the space more energy than the smaller one, right? Because it's coming out of its area, which is much bigger. In other words, if you take the 40 watts light bulb and put closer to you, and you take this gigantic display of light producer and put somewhat away, you might even um, manage to see this bigger uh, uh, producer of light somewhat brighter than the 40 watts that is next to you. What I'm trying to say and picture here is when you think about stars and when we think about energy they're putting out, the energy depends not only on their size, so bigger, they have more area to emit photons or particles of light, so it depends on their size, but also depends on their temperature. So when we study light, we saw that photons or particles of light, they are more energetic. They are peaking and associated with high frequency, like UV, X rays, ultraviolet. They are more energetic than microwave or radio photons, right? So the energy is different depending on which frequency you are probing. And what we are going to learn in this chapter is that hotter stars, they tend to produce more radiation, more energy in in the shorter wavelength, in the higher frequency end. So the hotter the star is, the bluer it appears to us as we observe the star, and the cooler the star is, the redder the star appears to us as we see it in the night sky. Again, so if you have two stars, same size, and one is 10,000 Kelvin, the other is 3,000 Kelvin, imagine they both have the same size. So which one will carry or produce or send out more energy? It is the blue one, because they have the same size, and the blue one has photons or produce photons. They are more energetic. Now, if you take this blue star of some size and the star that is red, same size, and now you expand the red star to a fantastic diameter that is 100 times or 1,000 times bigger than the one that is blue and smaller. Now, which one will put out more energy? Well, when you sum all the possible energy, the photons that coming out of these two sources, you are going to find as final conclusion that the bigger the star is, although cooler, is the one more energetic. So it's the one that is sending out in a given time more energy in the space, and therefore you might be able to see the star even from afar, even from far away, because it is too energetic, although it's red. Okay. So when we go in the night sky and sit down on the grass and hear the crickets and smell the perfume of flowers and look up to the sky, and then you see all these stars of different colors, maybe if the sky is good, but we see stars of different brightness. We really don't know. We really don't know um, their sizes. We really don't know how close they are from us. What we know is that, statistically speaking, those stars we see in the sky, we see them because they are big, because they are luminous, because they produce a lot of energy. So the sun is our star that is close to us. Is not the most energetic star out there, but it happens to be so close to us that is the brightest one. And the brightness is such that during daytime we don't see all the stars because the sun's radiation washes them out. At nighttime, the sun is not in the picture, then we might be able to see them all. So luminosity and apparent magnitude, please, those are two important quantities. Now, what is the magnitude scale? So in the 1900, and pretty much mimicking the scale Hipparchus have put it out. Um, Hipparchus classified a long time ago. He classified the stars by their apparent brightness. So stars he could see well, he addressed a number, magnitude 1. Those are the brightest star in the sky. So magnitude 2 were those that are roughly half as bright as that one. And then have magnitude 3, which was roughly as half bright as the magnitude 2 star. And he went that way all the way to magnitude 6, which were those stars you could barely see it. Now, this scale was, in fact, converted to a more precise mathematical scale using logarithmic function, and then we have the magnitude scale that is largely used in astronomy nowadays. And the way it goes, the change in magnitude number in this logarithm scale. So you go to magnitude 0 as a star that is sufficiently bright in the sky. And when you observe a star that has a magnitude 1, so it's one number above 0, right? 1 is a number above 0. That star is less bright, has a brightness that is equivalent to a number less bright, not a factor of 2, but a factor of 2.5 something. There you go, 2.5. So at least you don't need to go to a lot of detail, but when you compare now a star of magnitude 2 with a star of magnitude 1, the magnitude star is 2.5 less bright than star magnitude 1. So therefore, when you compare star magnitude 2 with the star magnitude 0, the star magnitude 2 is 2.5 times 2.5 less bright than a star magnitude 0. Right? So it's 6.25 times. So which means if you take 6 stars magnitude 2 and put them together, you might be able to match the brightness of a star magnitude 0. Whether they get 6, well, because 2.5 times 2.5 is 6.25, right? Something like that. Okay, 6.25. So I'm rounding up to 6. Now, this magnitude scale, what do you need to know? You need to know that as you go to smaller number, you are probing stars that happen to be bright in the sky. Look at the sun, for instance. The sun is somewhere between negative 25 and negative 30. So the sun has this least number here in the scale, which means it's the brightest object in the sky. And let's take, for instance, what is Venus? Venus is very bright. You can see in the sky in the afternoon or after sunset. The magnitude is only outshined by the moon itself and the sun. So a full moon can be as bright as somewhere a number between negative 10 and negative 15. So 6 is the limit to what we can see it. So a star's magnitude 7, we can't see in the night sky even under perfect conditions. Okay. So this magnitude scale can be converted in brightness. And here's the conversion factor. That's the number 2.5 that I was mentioning. And these numbers, integer numbers, are identified as a logarithmic numbers. So I don't want to go there with you. We do in the labs, but not in our astronomy descriptive. But you should be able to distinguish what is bright and what's not based on the magnitude. Let's say few colleagues like to observe stars magnitude 12 because they represent stars that are in formation, and so when you say these numbers, you know how bright they are, and if you are a skillful observer, you know how many minutes you should point your telescope to in order to have a decent signal of that star. So colors. So what colors are? So here in this picture, you can see something phenomenal. So we have stars. Some of them are clearly red and some of them are clearly blue. And so the blue stars are, as I mentioned, the hotter they are. And the redder they appear to you, the cooler they are. The reason for that is the stars and the gas around them behave like what we call black body. I'm not going to go in detail of what a black body radiation is, but it was a major part in the history of physics and modern physics to determine what a black body exactly was. And Max Planck was the one who came up with explanation, assuming that the walls of a gas that behaved like a black body would be able to absorb radiation in a very selective way, not in a continuous way. I cannot go in a lot of detail here in the class, but just to say that the black body is something that is able to absorb energy in all possible frequencies, and when it absorbs that energy, it spreads out in all possible frequencies. So it doesn't reflect. That's the main point. For instance, if you take uh, the white light that comes from the sun, and as we saw previously, the white light is a combination of light of different frequencies or different colors. When the white light hit, for instance, the blanket I have in front of me that's red, the material the blanket is made of absorbs everything but rejects the red, and then we see that as a red color. So black body are not objects reflecting radiation. In fact, they are objects producing radiation. So let me show you here one example that might be able to illustrate what I'm trying to say with respect to black bodies. Again, if you go to the Nebraska Astronomy Applets, I really like this source, and they have very good applets. We can have a display of what a black body is. So here's a black body. It's a curve, and you might think, why do I need to know about curves? Well, because let's say this curve represents a black body at 6,000 Kelvin. Kelvin is a scale of temperature, and our sun is pretty much close to 6,000 Kelvin in average surface temperature. So if you take this the sun's surface temperature and you measure altogether in its average, you would get some number close to 6,000. And what is being shown here, that this curve of a black body that is representative of 6,000 Kelvin doesn't produce a lot of radiation here in the ultraviolet. But most of its emission, as you can see here, most of its power, if you will, most of its intensity comes from this greenish part of the spectrum, right? So if I increase the temperature of a black body, let's say if I look at star that is 9,000, that star, 9,000 Kelvin, like Vega, it's a 9,000 Kelvin star. Vega is going to be peaking, most of its radiation comes from the far ultraviolet radiation, as you can see here. And if I go to Antares, which is a red supergiant, about 3,000 Kelvin its surface temperature, most of its radiation comes pretty much in a nanometer or the microwave type of wavelength, in the infrared, if you will. So it has optical radiation, but see, if you look at the star, and here's the optical range, the star will be sending out more radiation in the red part of the spectra than it is in the blue. So looking at Antares, you see kind of a reddish star, right? And when you look at Vega, which is about this temperature, most of its radiation, if you look at optical range, which is this rainbow here, so it is more radiation coming out of the ultraviolet part of the star will appear reddish. So astronomers were able to explain in very good detail, at least using a quantic model, how black bodies behave, and that's how we understand stars nowadays. Another example of a black body is this example over here. So this is a circuit. It's been showing a circuit. You have the handle here. Is a nail, right? And somebody has a light bulb that is shining on it, and 300 Kelvin is the local temperature, basically. Kelvin is a scale that is given by Celsius scale plus 273.5 0.15 Kelvin. So, which means at 300 Kelvin, the temperature, the ambient temperature is 27 Celsius, which is a very nice, mild temperatures, 70 or so um, Fahrenheit. So you have this nice temperature here, and this is a circuit connected to a battery. And what I will do, I will start this phenomenon, and then the light will turn off, and there will be just current going through this circuit, and this current will warm up the nail, and eventually the nail melts, and then the circuit is broken. So see what happened. So the light is off, and now the nail warms up, and its color keeps changing as the temperature rises, right? The temperature is rising, the color is changed, now it's a bright yellow, and eventually the circuit breaks. There you go. Uh, if this procedure would be allowed to continue, eventually the nail would melt and and would vaporize. That's what happened in stars. In stars, the gas, the solid, is not, because it's all plasma. It's all vaporized, and then the vapor, due to their high temperature, is pretty much ionized, and then you can say that stars are indeed plasma of gas. It's a combination of ions um, and metal. And here you can see the black body curve changing as the temperature of the nail increases. So this is a black body. It's an object that is producing energy. It's not just reflecting. I have a blue shirt here. This blue shirt is not a black body that is hot at a 10,000 Kelvin. Not at all. I would be completely dead. So it's blue because the white light the sun produces out is being rejected by this material, whereas all the other frequencies are being used by the material of my shirt or t-shirt to operate its chemistry. And here is how this temperature relates to the dominant color of the star. So this is a simple way. A student with some training abilities can look at star with the telescope, and based on the coloration the star has, it can kind of tell with some plus or minus 500 Kelvin, can indicate what is the average surface temperature of that star. So more detailed calculations can be done if you use a technique in photometry that allows you to measure the brightness of a star as seen from different color filters. Color filters. Um, and this technique is a little bit more specific. So, but basically, what you do, you take the star you want to observe, and you observe it with a, let's say, a blue filter, and then you have a measurement of how bright that star is with the blue filter, and then you do the same with the visual filter, with a filter that is blocking out all radiation except that can go through the visual color band. And then you see how bright the star is. And then you do the same with the red filter. It's one that blocks out everything except the red part of the spectrum. Now, you measure how bright the stars is, and now by using techniques and some little math that a graduate student that is on track to become astronomers learn, you can use the ratio, or more saying the um, not so much the ratio, but you can use these numbers, or the brightness, better saying, that you obtain from each filter. You can use that information, the ratio of that information, to pin down the stellar surface. Okay, so the stellar surface temperature, I mean. So you can have a very sharp determination of surface temperature by observing with filters the stellar the star atmosphere. Now you can techniques and during the 20th century, astronomers use different ranges of filters, and with uh, playing again, or not better saying not playing, but by using the brightness or the ratio of brightness in different filters, astronomers were able to really know more about the stars, not only temperature, but also metallicity. What type of metallicity the star is going through. So you can build filters that allow information on certain transitions to go through certain dark lines, as we studied previously, and by doing so, you can determine how certain metals behave in the star. What is the metallicity? What is the metal content of certain stars? Now, this goes without saying about spectroscopy. Let me see if I have here a spectrum of a star. Just a second. Oh no, I deleted. Um, but spectroscopy is a science by which you take the stellar light and you make a rainbow of it. And by doing a rainbow of it, you can classify the star by the strength of certain dark lines. And this task was accomplished by a battalion of women in early 1900, hired by Alfred Pickering in Harvard. And they were able to create a spectral classification. That's the one we use right now. OBAFGKMLTV. Oh, be a fine girl or guy, kiss me. That is how I learned spectral classification in school in my young days, and that's the sequence you can read in several books. But now you have an extended part of the M group, those that are even cooler than M stars, and they are pretty much associated with brown dwarfs, with stars that are not producing fusion reactions, hydrogen fusion reactions in their core, but they they are still under classification. So, for instance, an O star is a hot star. So if you look and identify an O star in the sky, it will appear to you as a bluish star. And and if you do spectroscopy of it, which means if you take the star, make a rainbow, and spread that rainbow out so that you can see in detail absorption lines, you see lots of helium lines, weak hydrogen lines. So let me see if I can show you a spectra here, so that you know what I'm talking about. Let me take the spectra of the sun. Let me get a spectra of the sun. This is a graphic indicating a dark lines. So dark lines. Remember dark lines we studied previously? So what's being shown here, this big depression right here, is caused by hydrogen lines. In fact, this is a transition called hydrogen alpha, Balmer alpha. It's very common in stars in general and is more strong in A star in that classification and and become very weak in O star, the hot one. This is the spectrum of the sun. The sun is a G star. Remember the classification O, B, A, F, G star. The sun is a G star too, and those spikes, these lines going down here, are also solar lines. Are also solar lines um, representative of specific metals. So let me expand this so we can see with more detail some of these lines. The scale here is in wavelength, and I will have a display in wavelength from uh, 6,500 angstroms to 6,600 angstroms, 100 angstroms. It's a long one, and I will display this now with a smaller scale so we can see these lines with more detail. So a student or a professional that work with spectroscopy knows which lines those lines represent, which transitions, transitions um, inside atoms, which one they are. So atoms of certain elements like iron, calcium, zinc, um, strontium, titanium, vanadium, um, they are responsible for every single one of these lines. And astronomers, by identifying first the lines and knowing how broad they are, how deep they are, if they have any asymmetry, if they have some blend with something else, astronomers can then refer to um, processes that are happening in the stellar atmosphere to that impact the symmetry of these lines. And by modeling line formation, they can um, indicate and predict how the gas in the stellar atmosphere behave. So again, spectroscopy and photometry, those are the tools that allow us to do all the measurements. There are important in this chapter, and tomorrow I will be talking a little bit more, is the inverse square law. The inverse square law, let's see if I can get that. The inverse square law is one that if you happen to know the luminosity of a given star, which means how luminous a star is, because you know how, or you have identified characteristics of these stars in a group. So, but you know how much energy that star is sending. If you observe that star, you can use the inverse square law to determine how far the star is. So distances, as well as mass, as well as radius, can all be taken care and accounted for when we studied the HR or Hertzsprung-Russell diagram. So tomorrow I will be focusing on Hertzsprung-Russell diagram, and also tomorrow we have our midterm number 2, and as it started midnight if you are doing online, but I will be available um, in in room SA 111, begin at 4 o'clock. You can arrive there earlier. In fact, I will be there since 3:30. If you get there 3:30, 3:45, you can start your exam and get out of there in room SA 111 tomorrow. Okay. Any question? All right. All right. Good night to all of you, and thanks for coming.